Okay, in this demo, we're going to learn about atomic spectra, how each individual chemical element has a unique fingerprint in the light that its electrons will emit when they're changing energy levels. So let's first look at this incandescent bulb. It has white light. White to our eye is what we call an almost equal mixture of all the colors of the rainbow in the visible part of the spectrum. So if I take my diffraction grating and bring it up to the camera here, I'm creating a spectrum of that light, and you can see there that it has purple, blue, green, yellow, orange, and red wavelengths in it. That's our first order spectrum to one side of the light bulb. We can actually move to the other side of the light bulb and see the first order spectrum on the other side, where purple is closest to the source and red is farthest from the source. And that's the same is true on the left-hand side. So let's take a look at a chemical element. The lamp that I have in question here is hydrogen, and what we're going to do is shut off this bulb for a second so we're not swamped by its light. And in this narrow tube is hydrogen gas. So what I've done here is put a few thousand volts of electricity across the ends of the gas chamber there, and that electric field is giving the electrons so much energy that they're being unbound from their atom, and they're floating free briefly, and really quickly they will descend, find another atom and descend down into lower and lower energy levels. So remember, quantum mechanics says that they don't always just go from being free down into the ground state. They might come down to n equals 5, say, the n equals 5 state, the fifth highest energy level, and then jump down to n equals 4, and then to 3, then the 2, then the 1. Or maybe they jump from 5 directly to 1. There's some probability that they do that too. So let's take a look and see what the electrons are doing with our hydrogen atom here. I'm going to put the spectra up. What you can see is a prominent red line, a prominent aqua-colored line, and a prominent blue-colored line. Okay. There's a purple line there too. It's just too faint to observe. Okay. So what's happening to create the red line is that electrons find themselves in the n equals 3 level, and they jump from 3 to 2. That's called the Balmer line of hydrogen. The Balmer series of hydrogen when they jump from a higher energy state down to n equals 2. So they end up at n equals 2. So the one with the lowest energy there is when they drop from n equals 3 to 2 to create that red line. It's a very important line for astrophysicists because most of the universe is hydrogen gas, and studying the strength of that line tells us how ionized a gas is. It can tell us temperatures. It can tell us the physical conditions of the gas where we can't travel there and actually sample it. So that aqua-colored line is a little higher in energy, so it's bluer in the spectrum. And the aqua-colored line there is a transition from n equals 4 down to n equals 2. Remember, if an electron finds itself in the n equals 4 state, it doesn't have to jump all the way down to n equals 1. It can jump down to 2 or 3. It has a couple of choices there. So quantum mechanics will actually allow us to evaluate how often, what the probability is that an electron in the n equals 4 state will jump down to 2 or 3 or 1. But in this case, in the aqua-colored line is every time an electron jumps from 4 down to 2, it lets off that color light. And then that bluer colored light comes from n equals 5 down to n equals 2. All the other from higher n's than 5 down to n equals 2, those energies are of course higher in energy, and they're actually in the ultraviolet part of the spectrum, and so we can't see it with our eyes. We'd have to use an ultraviolet telescope and an ultraviolet detector to make a recording of the light that's emitted there. But remember, while the electrons are jumping down to n equals 2, they're also then jumping back down into n equals 1. And that energy difference is even bigger than the line shown here in energy. And so again, that'll all happen at the infrared part of the spectrum. Okay, so that's hydrogen. 3 prominent lines in the optical part of the spectrum. So let's do the next most complicated element with neon. So, with helium here. The next element we're going to show you is helium. And you can look and see it's letting off an orange colored light, so we can guess there's going to be more emission lines in the orange and red part of the spectrum than there is in the blue or the green part of the spectrum, just by analyzing the mean color of the light there. So let's take our diffraction grating up, take a look at the spectrum, and we see indeed the brightest line is yellow. There's orange line, there's red lines, but indeed there is some aqua-colored and blue and purple lines. So helium is a more complex element. It has closer spaced energy levels, and a lot more of the transitions happen in the visible part of the spectrum. So now you can tell the difference between helium and hydrogen spectroscopically. If you see something that has yellow emission, you know it potentially could be some helium in there, but it's not entirely composed of hydrogen, because hydrogen wouldn't have that yellow line. All right, so let's take a look at neon. Let's turn this off. So neon, when we just look with our eyes, it looks much more orange and red. So we know that the light coming off, most of it's going to be in that region of the spectrum, as opposed to blue or yellow, blue or green light. So let's take a look at the spectrum. Here is the spectrum of neon. There are so many lines piled up on top of one another. It looks like almost a continuous band of yellow light there, with some orange and some red light too. But no prominent, just maybe one very, very faint green line of neon, and no blue or purple lines. So this is the way spectroscopists tell the difference between different chemical elements. Each element has a unique signature, and by measuring it, shocking the electrons, letting them fall back down into their energy states, and measuring the light that comes out, we can actually determine the chemical composition of a gas, even if that gas is all the way out in the sun or in a distant galaxy.